So in this video we want to introduce the idea of a level surface. It's an idea that we're going to need to use when we develop the equation of a tangent plane. So we just want to make sure that we understand what a level surface is. So we've already looked at level curves. And when we did level curves, we had functions of two variables. So for example, we had f of xy equaling, let's say, just the x squared plus y squared minus 9 piece of this. So x squared plus y squared minus 9. And this is a surface in three-dimensional space. If we graph it, we get a paraboloid. And when we took level surfaces, what we did is we took values for c. For example, c equal 7, c equals 16. We could do c equals 0. And we took our equation f of xy, and we set it equal to those different values. F of xy equals 7, f of xy equals 16, f of xy equals 0. And then we replaced our function f of xy with those constant values. So for example, if I replaced f of xy with 7, we would get 7 equals x squared plus y squared minus 9. We can add 9 to both sides. We get 16 equals x squared plus y squared, and we get a circle of radius 4 in the xy plane. So what we identified when we were doing level surfaces is we were really taking the plane z equals c, cutting the surface with that plane, looking at the trace of the intersection of that horizontal plane with the surface, and then projecting that trace down into the xy plane. And we would do it for several values of c. And we got curves literally in the xy plane. For the case of the paraboloid, we got circles centered at the origin, so family of concentric circles depending on how we pick values for c. So a function of three variables is actually going to live in four-dimensional space. So here I have a function of three variables. So just like a function of two variables, because it's z equals that function, you're getting order triples x, y, z. Well, this would be w equals big F of x, y, z. So to plot this, you would need to plot four values. The x, y, z would be your independent variables, and you would have a dependent variable output, call it w. And so you'd have four coordinates, which would need four-dimensional space in which to plot them. So the idea is it's difficult to graph big F of x, y, z. But we can see what its level surfaces look like. So for example, if we take and set c equal to constant values like we did here, c equals 7, c equals 16, c equals 0, and then we set our function f of x, y, z equal to those constant values like 7, for example, then we would get 7 equals x squared. We've thrown in that extra component, x squared plus y squared plus z squared minus 9. Add 9 to both sides. 16 equals x squared plus y squared plus z squared. We actually get a sphere of radius 4. With a paraboloid, we got a circle of radius 4. So as we step up a dimension, the three-dimensional analog of a circle is a sphere. So now instead of a level curve that lives in the plane, we have a level surface living in three-dimensional space. When we take our function and set it equal to a constant, we get level surfaces. We get three-dimensional objects. And when we develop the technique for finding planes that are tangent to a surface, the idea of level curves is going to be particularly important, and we're going to be particularly interested in the case where we let c equals 0, and we look at the level curve f of xyz equals 0, which in this case, if I replace the function here with a 0, I get 0 equals x squared plus y squared plus z squared minus 9. Add that 9 to both sides. In this case, for the level curve big F equals 0, we get a sphere of radius 3. So that's all a level curve is. As we move up a dimension from a function of two variables to a function of three variables, instead of level curves living in the xy plane, we get level surfaces living in space, in three-dimensional space.